our second foray into energy is going to be talking about light. Okay, light, photons, is light that represents what we can see. Two general types of energy. One is thermal energy, the energy of things in motion, and the other one belongs to light. Okay? So we have to look at how energy is associated with light and how the nature of light works and how we can calculate energetic values and how we describe light, that kind of thing. All right? So the first thing that we need to know about light is we know that the speed of light has been calculated and it's derived from two variables. Lambda times nu. Okay? The speed of light, which is c, turns out to be about 3.00 times 10 to the 8th meters per second. Okay, notice it's a velocity. It's a really high velocity. This lambda value, that lambda represents the wavelength. Okay, and generally the wavelength is reported in meters. Okay, because it's a length, right? Wavelength. This funny term, this little nu thing, because it's like a sideways V, you know, it's kind of a swoopy V. That's nu, and nu represents frequency. Make a swoopy F for that. Frequency. And frequency is a funny little term because you have 1/2 to describe the units of frequency. Right? Another way of looking at this, another thing that we talk about with that, is hertz. Okay? Hertz is the measurement of frequency. So here we are, the three different variables are associated with it. And what do they mean? Well, let me draw a wave here on the board. Alright, so here's a wave. Alright? And you look at that and say, well, that's light traveling through something, a poorly drawn board. But if you've got light moving in this direction, we have to define what's a wavelength and what's frequency. If you draw a point which bisects halfway between each of these terms, what you have at this point is a point that's traveled through both the positive and negative domains of the light. All right? The plus and minus terms is a mathematical term, mathematical construct, indicating that we've got one full turn here. All right? This is a complete wave. So the wavelength is how long one of these terms is. Okay? So that's a wavelength. Frequency depends on how fast the wave is moving past a certain point. Okay? If I take this wave and I compress it to a certain degree, alright, once I compress this wave, alright, when I look at this, my wavelength has changed, when this means that also my wave is traveling through a fixed point in space at a greater count. Right? And that count is represented by hertz. Okay, so this is the frequency. It's how fast light is moving through a certain point. So, and you can tell by this equation that wavelength and frequency have an inverse relationship. The longer the wavelength, the lower the frequency. The shorter the frequency or shorter the wavelength, the higher the frequency. Okay? So these two things are pretty easy to analyze. If you are going to look at this with a mathematical calculation, note that C is constant. So I'm going to write C, or the C as a K, which is a constant here. Okay? And the mathematical abstract talks about X times Y. All right? X being wavelength, and Y being frequency. Right? And notice that if I rearrange this equation, I can get k over x, and that's going to be equal to y. And I can also get k constant over y is equal to x. So guess what? We can do that mathematically in the abstract here. We can do the same on the other side. Now, how did I get that? Glad you asked. If I just take this equation, right, and if I divide both sides by x, then the x is going to cancel here, and that's how I get the y isolated on one side. Okay, does all this come back to you at this point? Good. All right. So I can do the same thing over here. So c is equal to wavelength times frequency. If I divide both sides by wavelength, I get c over wavelength is going to be equal to frequency. Flip side of this is I can also have c over frequency is going to be equal to wavelength. All right, you see how I did this? This is important. These types of things are important because you're going to have to figure out how to manipulate these equations in order to get the terms that you need to solve a problem. Okay? Let's talk a little bit more about light. So here's a representation of the electromagnetic spectrum. And you can see the wavelength and the frequency that's associated with light. When most people talk about different types of the electromagnetic spectrum and the types of light that are involved, usually they're referred to in wavelength. Okay? So I'm going to refer to these things as wavelength instead of frequency. Up here, the wavelength gets very, very short, and that's where we get gamma radiation. We're also going to have high frequency light. This light up here is the most energetic. If you think about it, think about all the energy you've got to use to compress that wave to a very, very small wavelength. Okay? And in doing so, what you're doing is you've got to add there's going to be a lot of energy that's associated with it. If you think about frequency, the thing's going rather than radio waves, which are very long, progressive waves. Okay? So gamma radiation, highest energy radiation, as we move this way down the electromagnetic frequencies and wavelengths, we get down to these wavelengths down here. The wavelengths down here are like 10 to the 11th meters. Okay? So the wavelength that we've got here is in meters, and the image quality is terrible here. I apologize for that. But this one, this is nanometers, is what they've got here. So when you get to 10 to the 11th nanometers, at that point it's about 100 meters. So over here, you're talking about wavelengths that are in the kilometer range. Okay? When you get down here, this particular value was 10 to the minus 3 nanometers. So the wavelength is a picometer. It's a tiny, tiny little meter of value. Okay? That's gamma radiation at that point. And the energy that's resulting from high energetic light and gamma radiation is more dangerous and more troublesome than the radio waves. Okay? What we see with our eyes is right here in the visible range. Highest energy visible light is going to be in the violet, UV. Okay? UV is outside of our visual range, but you've all heard about it, right? Sunblock is used to block out UV rays. Yeah? Because that UVB that comes down from the sun is dangerous to our skin. It causes sunburns. Okay? It's higher energy light. As we move down into the red, okay, we haven't shifted much on the electromagnetic scale, but what we have done, we've changed colors over into the red. When we get into the red, like the infrared and the microwave, the wavelengths are getting pretty long. Okay? Now you've all heard those stories about don't stick stuff in the microwave, you don't bathe your cat and then stick it in the microwave. Right? It's bad for the cat. Okay, why is it bad for the cat? It's not because it's shooting gamma rays at the cat. What it's doing is it's using the microwave energy to excite the water that's inside the cat. So you're boiling your cat alive. So don't do that. Put it in the dryer instead. No, I'm just kidding. Don't put it in the dryer. Okay? You're going to towel off the cat. All right? Then we get down here to radio waves. Okay? Things like AM radios or television. The stuff that we get and for use for entertainment, music purposes. All this stuff's down here in the radio frequency. Right? Over here in the high energy range, X-rays, there's not really a good use for gamma radiation, so, except, killing your enemies, I guess, in gamma radiation, right? X-ray down here, sun lamps or the sun. Okay, the sun gives off all of this light, all right? But sun lamps give off UV. Okay, tanning booths give off UV, so be careful in tanning booths. Heat lamps, infrared, and microwave generators. You see in these cell phone towers, like cell phones, they use microwave radiation to communicate to each other. Okay. Now, one more thing I want to talk about with light, and this is the double slit experiment. All right. It kind of drives home the idea that light is a wave. And what they did with the double slit experiment, they took a light source, shone light, and they had something that was here. It just had one slit in it, and that slit starts propagating a wave. But behind it, you have something that's got another slit and another slit over here. As the light comes through here, it bends a little bit, okay, because it's going around an object. Right? As it bends, the light that hits here is going to bend as well, and it starts propagating these waves. Now, these waves, when they interact with each other, they're going to have two possible outcomes. Okay, they're going to be constructive or they can be destructive. Destructive waves means that they cancel out, and constructive waves means that they're additive. Okay? So what we ended up seeing with the slit, double slit experiment, is we had two outcomes. Right? We had areas which were dark, all right, and other areas that are actually seem to be more intense than their light source. Okay? So light. So instead of getting one big light pattern, what we ended up getting was sort of a staggering of these light forms. And what this meant is that we were having constructive and destructive interference. To give you an idea of what this is, okay, if I have two wavelengths, so here's wavelength number 1, and I'm going to put wavelength number 2 here. Okay? Now, for the purpose of argument, assume that the amplitude of both of these waves is the same. Now, if you look at this one's got a positive value and a negative value. All right? This one down here has got a negative and a positive value. When I combine those two wavelengths, what ends up happening is that the positive and negative, they've got to add together. What happens when you add a negative to a positive number? It's going to get smaller, right? Same thing on this side. So what I've illustrated here is destructive interference. The overall result of the wave that's associated with this is going to be a flat line. All right? If I do constructive interference, okay, notice at this point, my waves are going to line up. So at this point, my positive and my negative are going to be lining up with the green positive and negative. And as a result, when I squeeze those two things together, I get a larger wave. My wave function at this point, or my wave, is going to be an addition of the heights of both of those waves. So whatever the height of this one and this one is, the values are going to be magnified by 2. All right? So that's why, and this is constructive interference. The reason that this is important is because electrons also travel in the waves that we're talking about. So when these types of electron waves interact like light waves, they're going to interact in a very similar fashion. Okay, so you can expect there to be destructive and constructive electron waves, and those can be good or bad depending upon what you want to do with those.